Hey there, chemists. In this lesson, we are going to look at polymers and relate it to what we've learned about with radical reactions. Now, when we say polymers, we're talking macromolecules, really large things that interest scientists because of their physical properties as opposed to their chemical properties, which is what we're concerned with smaller molecules. You can break them up into two different categories. We're talking about natural or biopolymers, things like polysaccharides, which come from polymerizing small sugar molecules, proteins, which come from polymerizing amino acids, or DNA from polymerizing nucleotides. Then we get to synthetic polymers, things like plastics, moldable polymers. The first one ever made was celluloid back in 1856, made by taking the polymer nitrocellulose and mixing it with camphor. They used it in billiard balls and piano keys to replace what used to be naturally occurring ivory. Sometimes they were met with unfortunate circumstances, though, because nitrocellulose, which is nitrated cellulose, in other words paper, is highly flammable, as I'll show you right now. If you've seen this before, it burns very cleanly, but it is highly flammable, so don't use that any longer. Fibers are synthetic polymers. The first one ever made was rayon, and rubber's a synthetic polymer, a flexible, elastic polymer. So what does this have to do with radical chemistry? Well, some of these synthetic polymers are made through addition polymerization reactions, and they follow the same mechanistic paths that we saw for the substitution reactions. It all has to do with an initiation, a propagation, and a termination step. So I'll show you a little bit about that, and then we'll start to recognize how, what we learned about with small molecule radical reactions we can apply to bigger molecules. And studying polymers is a huge industry in chemistry to this day because now we have a lot more understanding about what goes into making a polymer. So scientists are actually engineering and designing specific molecules, macromolecules, and dialing in the properties that they want on a small scale to get something with a large scale that's useful for society. How it works chemically, let's say I wanted to look at the polymerization of just an ethylene molecule to make polyethylene. You start with an initiator, such as this benzoyl peroxide. This is the same chemical substance that they put in certain anti-acne medications. It's a bactericide. It also works as a radical initiator, and that's because of this very weak oxygen-oxygen single bond, which on its own can split like so, and give us two benzoyl radicals, which look like this. It's a benzene with a carbonyl and an oxygen radical. Now that doesn't stick around, that actually pretty easily collapses to make a CO2 molecule and a phenyl radical. Arguably you could put this all in the same step, but I'm showing it in multiple steps here. There's your phenyl radical, and then nice entropic driving force to spit out a gaseous CO2 molecule. So there's our radical initiator, and we can, or our radical propagator really for the next step. We could use this to polymerize a monomer. And in this case, we're just using the alkene ethylene, common name of ethene. And how does this work? Well, as soon as that very reactive radical sees the alkene monomer, it does an addition to the pi bond and adds two new carbons. I'm just going to say pH for phenyl, and you get a radical, one away from the carbon that's benzoic. But we're not done. This can keep going and see another alkene monomer, break that pi bond, and now I've got four carbons attached to that phenyl. And this could continue to go until effectively you have this very long chain of repeating ethylene units where the pi bond is gone, you're all sigma bonds, and it's capped off with a phenyl on one side and maybe another phenyl on the other, but frankly at that scale it doesn't even matter anymore because so much of the molecule is dominated by the properties of that repeating polyethylene structure. So they write this in a couple of ways. We could just write it like so, with a repeating zigzag hydrocarbon chain like that, or alternatively just show the repeating monomer unit inside a pair of parentheses, because that is a CH2 CH2, essentially infinitely repeating, and this is how we get polyethylene. And you can see what this is called addition polymerization, similar to the mechanisms we saw in the previous lesson. You're adding a radical to a pi bond in this case, and it propagates until you force it to terminate. You might wonder, why don't we just draw a CH2 inside a pair of parentheses and show that? That would communicate the same information. However, it doesn't show what the monomer actually looked like. We like to show what the actual monomer was, in this case, a molecule of ethylene. So here's a chart that shows several examples of polymers. I ID'd them with their recycling codes that we use here in the US for different types of polymers for drinking bottles made out of polyethylene terephthalate, or polyvinyl chloride for toys, and frankly, a lot more than that. That's what you find in plumbing pipes as well, that when they're not metal and they're plastic, they're made out of that PVC, that white PVC polymer. Polystyrene, a common styrofoam containing polymer, if you've ever worked with that. So here's just a couple of examples down at the bottom that show how addition polymerization works. They're all alkene monomers, and if I were to draw what the polymer looked like for each one, a repeating polypropylene unit, it's just the alkene that repeats, and whatever's attached to the alkene is along for the ride. So I'll pretend I have 3 of them, and I polymerize them infinitely. There's my 6 carbons, and on every other carbon I would have this methyl attached. So I'll draw it straight up, 1, 2, 3, and then those continue sort of infinitely, and I could draw it in the other fashion where I have a CH2 attached to a CH methyl in a repeating chain. Similarly, polystyrene, same kind of thing. I'll just skip right to the product. 2, 4, 6 carbons attached infinitely, and on every other carbon I have a phenyl, and that gives you polystyrene, much bigger molecule, and the whole point is you get different properties based on what you have attached to your monomer. So this would be a repeating CH2 unit and a CH phenyl. This is frankly the more common notation that we use when we write out the formula for a polymer. You'll probably see that in textbooks more than anything else, so I'll stick to just that. Teflon is made out of tetrafluoroethylene. In fact, it's polytetrafluoroethylene. It's just like polyethylene, but every single carbon has 2 fluorine atoms instead of hydrogens. This is what we use for non-stick cookware. Vinyl chloride polymerizes to become polyvinyl chloride. So I have a repeating CH2 and a CHCl. And then a synthetic fiber, acrylic fibers are made from polymerizing acrylonitrile, which looks like this. Again, it's the alkene that polymerizes, so there's my repeating chain with 2 H's on one carbon, and H and a nitrile on the other. There's tons of examples of this, and you can polymerize things other than alkenes, but these are the ones that primarily follow the types of arrow pushing that we saw with radical reactions.